Well, after the stability factor, the next point is bias stabilization techniques, which is also known as the biasing circuits. So let us first of all define what is bias stabilization. The definition of the bias stabilization says that it is a process of stabilizing the operating point. That means with the help of one of the techniques or the biasing circuits, which I'm going to mention, make sure that location of the operating point is at the center of the DC load line. That means under any circumstances, uh, ensure that this operating point does not shift towards the cutoff region or towards the saturation region in the output characteristic of the transistor when the transistor is in the common emitter configuration. So when we connect transistor in the common emitter configuration, and if we want to get the amplifier function from the transistor, then the transistor should be biased in such a way that it must act in the active region, right? So operating location of the operating point should be at the center of the DC load line, right? So the biasing circuit is required to keep the operating point stable on the DC load line. So as I said that DC load line is present on the output characteristic of the transistor, which is between the two output parameters. One is the output voltage and the second is the output current. As well as in the previous section also we defined the DC load line, and we also understood the operating point. Operating point is the location on the output characteristic, right? So operating point is the point which has the coordinate like Q. uh, X-axis coordinate is the output voltage, that is VCEQ, and Y-axis coordinate, that is the output current ICQ. So this is the location of the operating point on the output characteristic, right? What are the requirements of this biasing circuit? Let us discuss that. To establish the operating point Q at the middle of the load line, as I said that these stabilization techniques will uh, help us to keep the operating point Q at the center of the load line. Second requirement from the biasing circuit is to stabilize the collector current against the variation in the temperature. Uh, Make sure that magnitude of the collector current does not change with respect to the variation in the temperature. That is the stability of the collector current. Why? Because if the collector current gets changed, then you can see that operating point also gets changed, right? That means location of the operating point gets shifted from one point to another point. So we have to also make sure that collector current also remains constant even though if there is change in the temperature parameter. Then the third requirement of the biasing circuit is to make the operating point Q independent of the transistor parameter, right? So we have gone through the many transistor parameters, but we have to make sure that this value of the operating point Q, that means either IC or VCE, both of them uh, should be independent of the other transistor parameter, right? So we can stable the operating point Q. So these are the requirements of the biasing circuit. Let us go through the biasing circuit. So these are the basic biasing circuit defined in the slide. Right. So the first one is the fixed bias circuit. Second biasing circuit is the collector to base bias circuit. And the third one is the voltage divider bias circuit. So let us understand each one by one, starting with the fixed bias circuit. So here is the diagram of the fixed bias circuit. It is also known as the single base resistor bias or the base bias circuit. You can see that NPN transistor is in the common emitter configuration where the emitter terminal is the common between input base terminal and the output collector terminal. So base terminal is the input terminal and collector terminal is the output terminal for this circuit. And base terminal is connected to the DC supply VCC through the current limiting resistor RB. That means input terminal is biased by the DC supply VCC. Same way, the output terminal collector is supplied by the same voltage source, same DC voltage source, but through the current limiting resistor RC, which is in the collector terminal. And the transistor parameters, the current flowing through the collector terminal is IC, current flowing through the base resistor is IB, then voltage drop takes place between collector and emitter is VCE, and the voltage between the base emitter terminal is the VBE. Right? What is the key point about this fixed bias circuit? This is the simplest form of the biasing arrangement. Right? Compared to other biasing circuit, this one is the very simple arrangement of the biasing. Okay, let us analyze this circuit in detail. So you can see that here the input section is redrawn from the main circuit diagram. So while analyzing input and output section, we have to make sure that certain procedure we have to follow, right? So what is that procedure? While doing the analysis of the input section, we have to keep the output section as an open. That means you can see that here the collector terminal is output terminal. So when we go for the analysis of input section, then output terminal we have to make as an open terminal. That means whatever the resistor is connected, whatever the DC supply is connected to that terminal, disconnect all them and keep that terminal as floating, as open, right? No supply is given, no resistor is connected. Here you can see that. Similarly, while analyzing the output section, we have to keep the input section open. Input section open means we have to keep this base terminal open, right? So when I will redraw the output section, at the time you will understand in a better way. But this is the procedure. So while analyzing the input section, output section or output terminal is kept open. And similarly, while analyzing the output section, the input terminal should be kept open. So here we are doing the analysis for the input one. So output collector terminal is kept open. Right? So why are we doing these things? Why are we analyzing the input and output section? We are analyzing input and output section to get the mathematical expression for the operating point Q, right? So previously I showed that operating point is the coordinate, is the point on the output characteristic of the transistor, where the output characteristic is between output parameter VCE and IC. So you can see that I can write down the coordinates for Q point. That Q point is nothing but the VCEQ and ICQ. So to find out this operating point, we need the mathematical expression for each of these coordinate, that is mathematical equation of VCEQ and the mathematical equation of ICQ. Right, collector current corresponding to the operating point and collector emitter voltage corresponding to the operating point. So these will give us idea about the location of operating point on the output characteristic of this transistor. So to derive these operating point characteristic, we have to do this input and output analysis, right? So that is the reason behind doing this analysis. So for the input section, when we apply the KVL, that is Kirchhoff's voltage law, then we get the equation that is VCC is equal to IBRB plus VBE. How do we get this equation? That equation we can get by applying the KVL. at the input side. Input side, that is going from minus to positive terminal. So we get the first term as plus VCC. Then through this RB resistor going from the positive terminal to the negative terminal, the voltage drop takes place across RB resistor is defined as IB into RB. But as you can see that we are moving from positive terminal to negative terminal, so that voltage drop is in the negative form. And going from this positive base terminal to the negative emitter terminal, the voltage drop takes place between base emitter is equal to minus VBE, right? So the equation is like VCC minus IB RB minus VBE is equal to 0. So that is what we get when we apply the KVL at the input section, right? So from these equation, we can derive this one. How to do that? We will send this IBRB term on the right hand side. So on the left hand side, only VCC and VBE, these two terms remain. So VCC minus VBE is equal to IB into RB. And then divide that equation by RB on the both side, we get VCC, that is this one. Here you can see the equation, just a moment. That is this one. VCC minus VBE divided by RB. So when we make IB as a subject of equation into this equation, we get equation number 2, that is the base current, right? You might have questioned that we need IC and VCE for the operating point. Then what is the necessity to find out the base current, right? So to answer that, I would say IC, equation of the IC is, equation of the IC comes from the IB, right? So to find out the IC, we must find out the IB, right? Within few moments, you will understand what is the requirement to derive the equation for the IB and why do we need to do the analysis of the input section. So from this second equation, we may go further, but you can see that on the numerator of this equation, two terms are present. That is, first one is VCC and the second one is VBE. And normally the magnitude of VBE is equal to 0.7 volt, right? Because base emitter junction is in the forward bias condition and the voltage drop takes place across the forward bias diode is nothing but approximately 0.7 volt. And the magnitude of VCC is always in terms of tens, right? So compared to VCC, the magnitude of VB is very small. So sometimes for the simplification purpose, we may neglect the VBE. So if we neglect VBE, then the base current is approximated to VCC divided by RB, right? So here you can see that base current is approximately equal to VCC divided by RB when the VBE is very small. So from this equation number 3, we can write down the equation number, from that equation, we can write down the equation of IC, right? So the collector current in terms of the base current is derived by the equation IC is equal to beta DC into IB plus ICEO, right? This equation we derived when we went through the topics of the transistor, which is current components of the transistor and the relation among the different currents of the transistor. That means the relation between the base and collector current, relation between the collector and the base current, and the relation between the base and the emitter current, right? So from that topic, so in that topic, we derived the relation between the collector and the base current for the transistor, and in that we got this equation, that is IC equal to beta DC into IB plus ICEO. So whatever equation of the IB we derived in the previous slide, that we can substitute over here and we can find out the IC, that is one of the coordinate of operating point, ICQ, right? So From this equation, you can understand the requirement of doing the analysis of input section, that is to find out IB, right? If we are able to find out IB, then that means we obviously can get the IC, right? So IC is one of the coordinate for operating point. Then output section. So here you can see that while drawing the output section from the basic diagram, you can see that input section is made open, it is kept open. So here the base terminal is the input terminal, so base terminal is kept open, and the output portion, that is supply VCC, then current limiting resistor RC, which is connected in the output terminal, which is connected to output terminal collector, then output side voltage drop, that is between collector emitter junction, that is VCE, and emitter terminal connected to the ground. So this output portion is redrawn over here, and analysis of this circuit should be done. So how to do that? Same as the input section, apply the KVL in the output section, right? So when we apply the KVL, that means starting from the supply, going from negative to positive, that is plus VCC. Then this positive to negative terminal, the drop takes place across RC, that would be minus. And from going this positive terminal to negative terminal across the transistor, this drop VCE would be also negative. So this KVL gives us equation like VCC, then minus ICRC, and then minus VCE is equal to 0, right? So here you can see that when we make VCE as a subject of equation, that means let us take this VCE term on the right hand side. On the left side we have only two terms, that is VCC minus ICRC. So here you can see the equation number 5, that is VCE is equal to VCC minus ICRC. So that VCE is the second coordinate of the operating point, right? So equation number 3 and equation number 5, these two equations are the mathematical representation of the operating point, which gives us the location of the operating point on the output characteristic of this transistor. Right, so equation number 3 and 5 are the equation of operating point ICQ and VCEQ. So stabilization of the operating point Q. So the fixed bias circuit is the simple and easy to design, right? But still it is seldom used because it cannot stabilize the operating point. That is the biggest disadvantage of this fixed bias circuit, right? While starting this session, in the first slide, I mentioned requirements from the biasing circuit. So one of the requirements from the biasing circuit was that to stabilize the operating point. But this biasing circuit is not that much able to give us the stability of operating point, right? It is not effective as far as the stability of the operating point is concerned. So that is the biggest disadvantage of the simple bias circuit, which is fixed bias circuit. If the temperature increases, then the leakage current IC will change. Leakage current has direct relationship with the temperature. So whenever the temperature gets changed, the leakage current also gets changed. If the leakage current gets changed, so from the equation number 3, you can see that IC also gets changed. And if IC gets changed, that means the coordinates of the operating point gets changed, and ultimately the location of the operating point gets shifted from one point to another point, from one location to another location. So that reduces the stability of the operating point. Also, if the transistor is replaced by another transistor, that means if this transistor is replaced by same type of another transistor, that may happen that the beta of the first transistor and the beta of the second transistor may not be same, right? So if the beta gets changed, that means beta into IB plus ICEO, this answer gets changed, and ultimately IC will get changed. If IC will get changed, that means the operating point gets shifted from the required location to some another undesirable location. So again, changing the transistor also does not provide the stability of operating point in this fixed bias circuit. So because of these two reasons, these fixed bias circuits are seldom in use. They are rarely used in applications. So this is all about the fixed bias circuit, which is also known as the single base resistor bias or the base bias circuit. Now let us understand the collector to base bias circuit. So this is the basic circuit diagram of the collector to the base bias circuit, and on the right hand side the detailed diagram with all the components, all the possible parameters of the transistor, all the possible parameters of the transistor is shown, right? So what is the difference between this circuit diagram and the previous base bias circuit diagram? The difference is over here. In the previously discussed circuit diagram, the base terminal was connected to the supply VCC through RB, right? But in this one, in the collector to base bias circuit, the base collector is connected to the collector terminal through the RB resistor. So the difference between these biasing circuit and the previously discussed biasing circuit lies over here, right? So you can see that current through the RC resistor is nothing but the IC plus IB. Why? Because the IB is flowing through the base terminal and IC is flowing through the collector terminal. So there is a junction over here. So from this point onwards means on the upside, the current flowing in the circuit is nothing but the addition of these two divided current IC and IB. So the current from these starting from the supply to this junction is nothing but the IC plus IB. Both are together, and from this junction they get divided into two parts. The one which is flowing through the RB resistor and into the base terminal is the IB, and the second which is entering into the collector terminal is the IC, right? And same as the previous circuit diagram, the drop between base and emitter terminal is the VBE, and the drop takes place between collector emitter junction is the VCE. Now let us find out the mathematical expression for the operating point for these biasing circuit. That means we are supposed to find out the equation of ICQ and VCEQ, right? Because this is the common emitter configuration and the output characteristic which is between the output current IC and VCE. So we are expected to find out the mathematical formula of VCE and IC by analyzing the input and output section one by one. So when we redraw the input section for this main circuit diagram, you can see on the right hand side the collector terminal is kept open, right? So here you can clearly see the difference between the main circuit and the input section circuit. Only input section is highlighted and the output section, that is the collector terminal, is kept open. So VCC supply is there, then the RC is there, RB is also present, and the base terminal. So the direction of the current starts from the VCC, it passes through the RC, it passes through the RB, passes through this transistor base interjunction, and it goes to the ground. Right. So once again, let us apply the KVL, that is Kirchhoff's voltage law at the input side. So starting from the supply, that is VCC, then voltage drop takes place across this RC resistor. The upper terminal is the positive, the lower terminal is the negative, right? So when we go from the positive to negative terminal, then the voltage drop takes place across this RC resistor is minus RC into IC plus IB. Then this is also going from positive to negative, that is drop takes place across RB, and current flowing through the RB is IB, so minus IB into RB, and at finally the drop across the junction is VBE. So when we apply the loop, then the equation becomes like VCC minus drop across RC, that is RC into IC plus IB, then drop across RB because of base current IB, that is minus RB into IB, and from positive to negative across the base emitter junction, the voltage drop is VBE, that is equal to 0. So that what we get when we apply the KVL at this input side, right? So when we make VCC as subject of equation in this one, that means let us keep this VCC on the left side and let us send rest of the terms on the right hand side. The equation becomes 1. It looks like it will become like equation number 1, that is VCC is equal to, on the right hand side, RC into IB plus IC, that is this term, then IB into RB, which is this term. When this term goes on the right hand side, it becomes plus, and similarly when this term VBE goes on the right hand side, it becomes plus VBE. So VCC is equal to, when we open this bracket, then IC into RC, this IC gets multiplied to RC, that results into ICRC, then IB into RC and IB into RB. So these two term has IB parameter common. So let us take IB as common from these IBRC and IBRB. We get RB plus RC into IB and plus VBE, right? What we need IB. Why? Because this IB will help us to find out the IC, right? Because IC is equal to beta times IB plus ICEO. So we are supposed to find out initially IB. So from these, when we make IB as a subject of equation, when we send this VB on the left hand side, it becomes VCC minus VBE. Then when we send this ICRC also on the left hand side, it becomes negative, so minus ICRC. And this RB plus RC, which is in the multiply of IB, when we send this on the left hand side, it goes in the denominator. So the base current is uh, given by the equation number 2, right? VBE is equal to 0.7. The magnitude of the VBE is very far less than the VCC. So for the simplification purpose, we may neglect VBE sometimes. So at that time, IB is approximated like this: VCC minus ICRC divided by RC plus RB. And from this, we can get the first coordinate of the equation, that is IC. IC is equal to beta times IB, beta times IB plus ICEO, sorry, ICEO, right? So here you can see that equation number 3, that is one of the coordinate of operating point Q. Okay. Now let us redraw the output section. So while drawing the output section, you can see that uh, the input terminal base is kept open, right? Base terminal, which is which has the RB resistor, but here this RB is not connected to the collector terminal, right? It is not connected to the supply via this RC or the collector terminal. Input terminal is floating. It is 1. And output section, you can see that VCC, that is over here, plus minus, plus is connected to RC, that is over here, and negative terminal of RC is connected to the transistor, and the negative terminal of the transistor is connected to the ground, or you can say the negative terminal of the VCC. So this is how we can draw the output section of this connector to base bias circuit, right? So let us apply the KVL, Kirchhoff's voltage law, at the output side. So starting from this voltage source, we can write the equation like VCC minus IC plus IB when this current flows through this resistor RC, then the voltage drop takes place across RC is given as RC inside the bracket IB plus IC and drop takes place across the collector emitter junction, that is VCE is equal to 0, right? So this is our equation. From this equation we can easily sorry from this equation we can easily write this one, right? So by sending these second and the third term on the right hand side, we get the equation number 4, which is VCC is equal to IC plus IB into RC plus VCE. And from this equation number 4, when we make this VCE as a subject of equation, it means this term. When we make VCE as a subject of equation, then we get equation number 5, and which is nothing but the another coordinates of operating point. That is VCE is equal to VCC minus inside the bracket IC plus IB into RC, right? So as current IB is very much less than compared to IC, equation number 6 can be approximated to VCC minus IC into RC. What does that statement say? The statement says that the magnitude of IB is in terms of micro and magnitude of IC is in terms of milli range, right? So because of that, collector current is much higher than the base current. Because of small value of the base current, for the simplification purpose, sometimes we may neglect the magnitude of IB, right? So when we neglect the magnitude of IB, that means this IB RC becomes 0, and because of that, the equation number 6 results into equation number 7, that is VCE is approximately equal to VCC minus IC into RC. Equation number 7, which is the next coordinate or second coordinate of the operating point, right? So from equation number 2 and equation number 7, we can write down the equations of the operating point ICQ, which is beta times IB plus ICEO. We have to substitute this IB into this equation. Then after we can find out IC, and we have to substitute this. No need to substitute. VC is equal to VCC minus IC plus IB into RB. Yes, of course we have to substitute this IB into this equation, right? And IC from this equation into this one. So finally we get the VCEQ. Let us discuss the stabilization of Q point in collector to base bias circuit. Right, so how can we do that? Let us consider each of the scenario, the factors which may affect the location of operating point one by one, starting with the first one. If temperature increases, right? Previously I told that whenever the temperature increases or decreases, there is a direct effect on the leakage current, ICEO, right? So if temperature increases, then the leakage current ICE will increase. So if temperature increases, then ICEO increases, and if ICEO increases, then obviously IC gets increased. And if this IC gets increased, then what happens? If the collector current increases, then VC will decrease, right? Actually, that is VCE. VCE will decrease. What is the reason behind it? The reason is over here. If IC increases, then obviously VCE decreases. Why? Because this ICRC is getting subtracted from this VCC. So if IC increases because of increment in ICO, that is because of increment in temperature, VCE decreases. If this VCE decreases, then what happens? Obviously IB decreases. Why? Because IB is in direct relation with the VCE. If VCE drops, then IB drops. And if IB drops, then IC gets dropped. Right. So you can see that ultimately the net change in the collector current is equal to 0. Here the collector current increases, but at finally the correct collector current will decrease, right? So the temperature increases, which increase the leakage current, and ultimately the collector current increases because of increment in the collector current. Is VC gets increases because of the VC gets decreases. When VCE decreases, IB also decreases because of this relationship, and this relationship we derived in this base collector to base biasing circuit. And when IB drops, IC also drops. So that cycle is shown over here. You can see that temperature increases, the leakage current increases, because of that IC increases, and which results into drop in VCE, which results into a reduction in IB, and because of that IC reduces. So the net change in current IC is 0. So you can say that there is no change, so there is no effect of changing temperature on the collector current parameter. Or ultimately we can say there is no effect of temperature change on the operating point Q. Right? As far as the collector current parameter is concerned, ICQ is concerned. So hence, increase of the collector current due to the temperature will be stabilized by decrease in the base current. This is shown over here. Right? So second parameter, when we replace the transistor, what happens to the stability of the operating point? So as I discussed earlier, that whenever we change the transistor, then there is a chance of change in the magnitude beta, right? What is beta? Beta is the gain. So if the transistor is replaced by another transistor, then the beta DC may get changed. For example, if another transistor is selected and the second transistor has beta which is higher than the previous transistor, then what happens to the operating point when the biasing circuit is the collector to base bias? Let us analyze that one, right? So if the transistor is replaced by the another transistor and the second transistor is beta, which is greater than the previous transistor, that means we can say that the beta increases because of the replacement of the transistor. If beta increases, then obviously IC increases, right? Same as the previous slide. If IC increases, then obviously VCE also increases. If VCE increases, that means IB, sorry. If beta increases, IC increases, then IC increases. If IC increases, then VCE decreases, right? Because ICRC is the negative. So if ICRC, if this term increases, that means uh, result of this VCC minus ICRC reduces, that is VCE decreases. If VCE decreases, that means IB decreases, and if IB decreases, then ultimately IC decreases, right? So even though there is a change in the beta due to replacement of the transistor in collector to base bias circuit happens, there is no change in the operating point, right? Operating point is stabilized under this condition also. So that phenomena is also shown here without the equation. Beta increased, IC increased, because of that IC increased, and because of that VCE reduces, and because of that IB reduces, and ultimately IC gets decreased. So under these both circumstances, the collector to base bias circuit is providing us the stability of operating point Q, right? Let us move to the next biasing circuit, that is emitter feedback bias circuit. In emitter feedback bias circuit, here you can see that uh, base terminal is connected to the supply through the current limiting resistor RB. A collector terminal output terminal is connected to VCC through the current limiting resistor RC. But instead of connecting emitter terminal directly to the ground, the emitter resistor is present, right? So that is the difference between the first one, base bias circuit, and the bias circuit with the RE, that is emitter feedback bias circuit. So this one is the main circuit diagram of this emitter feedback bias circuit. So let us follow the as usual procedure to find out the expression for the operating coordinates of operating point Q, which are ICQ and VCEQ. And for that, we have to redraw the input section and redraw the output section and apply the KVL in each case. So when we redraw the input section, we have to keep these collector terminal open. So when we make that collector terminal open, and when we draw the rest of the components and rest of the parameters, the equivalent circuit becomes like this, right? So supply VCC, that is over here, then RB, which is here. RB is connected to the base terminal of the transistor, then transistor to emitter terminal, which is the common between input and output. But RE in this case is connected to the emitter terminal, and another terminal of the RE resistor is connected to the ground, which is nothing but ultimately the negative terminal of the supply voltage, right? So let us apply the KVL into this equivalent circuit diagram. So when we apply the KVL, the equation, it starts from the VCC. So from this, we're going from negative to positive, that is plus VCC minus IBRB minus VBE minus IERE is equal to 0. And when we rearrange the terms, we get the equation number 1, which is this one. VCC is equal to IBRB plus VBE plus IERE. And we are supposed to find out the base current, right? From that we can derive the IC, that is collector current. Why? Because IC is equal to beta times IB plus ICEO. So IB is equal to IVCC. How do we get second equation? The second equation can be found out by making IB as a subject of equation in the equation number 1. So when we want to find out IB, we have to send this VB and IERE on the left hand side. So you can see that VCC minus IERE minus VBE, and this RB in the denominator of that term. So we get the equation number 2. And we know that the magnitude of VBE is far less than the magnitude of VCC. So sometimes we can neglect this VBE for the simplification purpose, and IB can be approximated to VCC minus IERE divided by RB. So that is the equation for the base current. Right? And from that, we can find out the first coordinate of operating point, which is IC. IC is equal to beta times IB plus ICEO. Right? So to find out the expression for the second coordinate of the operating point, that is VCE, we have to redraw the output section. So for the output section, we have to keep the base terminal open. So here you can see that the base terminal is kept open. Starting from the supply VCC, positive terminal is connected to the RC resistor, then RC to transistor, and the transistor to RE, and RE which is connected to ground. It is ultimately nothing but the negative of VCC. So this is our output section. Same as the input section, let us apply the KVL to the output section. And when we apply the KVL, starting from the supply, VCC minus ICRC minus VCE minus IERE is equal to 0, right? So when we make VCC as subject of equation, we get the equation number 4, and from the 4, by making VCE as a subject of equation, we get the equation number 5, which is nothing but one of the coordinates of operating point VCEQ. So VCEQ is equal to VCC minus ICRC minus IERE, and IC, that is from equation number 3, ICQ is equal to beta DC into IB plus ICEO. right? So this is how we can find the coordinates of operating point and ultimately the location of operating point on the output characteristic. Uh, Once again, let us analyze the stability of operating point with respect to temperature as well as the change in the beta value. So first we will do the analysis of stability of operating point with respect to the temperature, and in the next slide we'll uh, analyze the stability of operating point with respect to beta. So what happens if temperature increases? If temperature increases, then the leakage current ICEO will increase, same as the previous case. So as ICEO increases, obviously IC increases, right? Because they are in the direct relationship. As IC increases, IE also increases, right? Why? Because IE is approximately equal to IC, and when IE increases, then from the base current equation we derived in this, sorry, it is not collector to base bias circuit, it should be emitter feedback bias circuit. So in emitter feedback bias circuit, we derived the equation for the base current. So when IE increases because of IC, IB reduces, and if IB reduces, that means IC reduces, right? So here the cycle is shown when the temperature increases. One, just a moment. When the temperature increases, the leakage current increases, and because of that, IC increases. If IC increases, IE also gets increased, and if IE gets increased, then the IERE drop takes place across emitter resistor increases, and because of that, IB reduces. That is from this equation, IB reduces, and because reduction in IB, IC also reduces. So the net change in the collector current is zero. That's right. So this emitter feedback bias circuit ensures the stability of collector current even though there is change in the temperature value. Right. Let us see the effect of second parameter on this operating point in emitter feedback bias circuit. Right. Actually, here there is a mistake in the title. It is the stabilization of Q point in a, a sorry emitter feedback bias circuit. Okay, so it is not for the collector to base bias circuit. It is for emitter feedback bias circuit. So let us analyze the change in beta DC due to replacement of transistor. What happens to the operating point? So if transistor is replaced by another transistor, then the beta DC may change. Let us take that beta is increased due to replacement of the transistor. Then what happens to the operating point that we are supposed to analyze? So if beta increases, obviously IC should increase, and when IC increases, IE should also increase, and if IE increases, then IERE increases, and because of that IB reduces. If IB reduces, then IC reduces, right? So when we look at the cycle, so in this cycle, you can see that when beta is increased, IC also increases. And when IC increases, IE increases. That is because of this relationship. And when IE increases, the drop across emitter resistor IERC increases. And when IERE increases, because of this relationship, there is reduction in IB. And when IB reduces, then because of this relationship, IC reduces. So here you can see that the net change in the collector current due to change in the beta because of replacement of the transistor in emitter feedbacks bias circuit is 0. That means emitter feedback bias circuit provides the stability of operating point even though you replace the transistor, right? So this biasing circuit is effective as far as the stability of operating point is concerned. The next biasing circuit is the voltage divider bias circuit. Let us first of all go through the key points about the bias, self bias of this voltage divider bias circuit. This is the basic circuit diagram, right? Uh, RC, RE, then R1 and R2. So these R1 and R2 gives us the voltage divider network at the base terminal, right? So you can see that the base terminal is connected between R1 and R2. R1 is connected to the VCC and here R2 is connected to the ground, right? So these biasing circuit is widely used in many applications, stabilizing the operating point Q against change in the temperature as well as the transistor current gain beta. So same as the previously discussed biasing circuit, these voltage divider bias circuit also provides us the stability of operating point against these two parameters. The first is the change in the temperature and the second one is the change in the beta DC, that is due to replacement of the transistor. The base circuit, that is this one, contains the voltage divider with R1 and R2 resistors. To simplify the circuit, it can be converted to Thevenin equivalent circuit, right? So to analyze the circuit and to derive the equations for the coordinates of operating points which are ICQ and VCQ, we have to convert this complex circuit into simple one by using the Thevenin's theorem. So Thevenin's equivalent circuit can be derived by finding out this Thevenin's equivalent resistor, that is RTH, and the voltage VTH, right? So by applying the Thevenin rule, we can find out RTH, VTH, and from that we can simplify this circuit diagram. So from the Thevenin's theorem, we can find out RTH, that is equal to R1 into R2 divided by R1 plus R2. That is by keeping the output section open, this R1 and R2 comes into the parallel, and when we find out the equivalent of these two parallel connected resistor, we get RTH is equal to R1 into R2 divided by R1 plus R2. Similarly, Thevenin's equivalent voltage can be found out by keeping this output section open. So the voltage drop takes place at this point, or you can say the voltage drop across these R2 resistor, or you can say the voltage at the base terminal is given as R2 divided by R1 plus R2 into VCC. So this is the Thevenin voltage equivalent voltage. So this circuit can be modified into this one using these two parameters. So at the base terminal, at the input terminal, we have the Thevenin equivalent resistor, and the base is supplied by VTH, which is derived from applying the Thevenin theorem. So this is our input section and this one is our output section, right? So this is the simplified version of this voltage divider bias network, and using this circuit diagram we will derive the equation of IC and VCE. So when we apply the KVL at the input side, we have to make sure that the collector terminal should be kept open. So here is the uh, equivalent circuit for the input section, and when we apply the KVL at the input side, the equation becomes like this one. Here the VTH, that is our Thevenin equivalent voltage, then drop across the RTH resistor. So RTH, because of the current flowing through it, IB, the drop takes place across base emitter junction, that is VBE, and then drop takes place across RE resistor due to IE current is this one, so is equal to 0, right? So this is what we get when we apply KVL at the input side. And by sending these all the terms except this VTH on the right hand side, we get equation number 1. That is this one, right? But what is IE? IE is equal to 1 plus beta times IB, right? IE is equal to 1 plus beta times IB. So we can substitute IE as 1 plus beta times IB. So we get equation number 2, and from equation number 2, when we make IB as a subject of equation, we get equation number 3, right? We are supposed to find out expression of IB to find out IC. So here, when we make IB as a subject of equation, we get this one, right? So let us do this by sending this VBE on the left hand side. It results into VTH minus VBE, and in the first term IB is present, on the last term IB, in the last term also IB is present, so we can take it common, and RTH plus 1 plus beta into RE. When we send these on the left hand side, it goes in the denominator, and by rearranging the terms we get the equation number 3, that is VTH minus VBE divided by RTH plus 1 plus inside the bracket 1 plus beta into RE. From this relationship, IC is equal to beta times IB, A plus ICEO, substituting these just a moment, yes, substituting this IB into this equation, we get the first coordinate of this operating point IC, right? ICQ. You can see that here one assumption is taken that beta DC is much greater than 1, and because of this 1 plus beta DC is converted as beta DC. That is the approximation. Value of beta DC is generally in terms of hundreds, right? So the 100 is far greater than the 1. So you can see that instead of writing 1 plus beta DC, it is much better to write only beta DC sometimes for the simplification purpose. And because of that, IB is approximated to VTH divided by this RTH plus beta DC into RE. So here the approximation is relevant to this beta 1 plus beta DC term. Okay, let us redraw the output section and apply the KVL at the output side and find out the expression for VCE. So while doing the analysis of output section, make sure that the input terminal, that is base terminal, should be kept open. So here you can see that base network is not present, but the output collector and the common terminal emitter network is present. Emitter portion is present. So VCC, then RC, then RE, and the transistor, right? So when we apply the KVL at the output side, we get the equation number 5, and by rearranging the terms, by making this VCE as a subject of equation, we get the equation number 6, which is nothing but the another coordinate of the operating point, right? So as I said, that operating point is the point which has the coordinates like VCEQ, that is x-axis coordinate, and ICQ, that is the y-axis coordinate, right? Values of these two, the value of these two, VCEQ and ICQ, decides the location of operating point Q on the output characteristic. What is that location on the output characteristic? So for that, let me once again show you that characteristic. That is over here. In the previous session, we went through that DC load line and operating point. That is, this is the operating point Q, right? So for operating point Q, we must know the x-axis coordinate, that is VCEQ, which tells us that operating point is this much far away on the x-axis, and the second coordinate of the operating point is ICQ, which tells us that the operating point is this much uh, value far away on the y-axis. Right? So by those two expressions, we can find out the magnitude of this VCE, that is distance, and the magnitude of ICE, that is this distance. And ultimately, we can look at the operating point in this output IC versus VCE characteristic on this DC load line, right? So that's it for this session. At least